Hi, I would like to welcome you to my session, the 2000 Watt Society and Passive House, as part of this summer's Life Cycle Summer School by FSLCI, supported by ACR Plus. First off, real quick, my thanks to Fritz and Philip for organizing the event, and we are honored to be part of this. My name is Tim Ayan. I am a principal at T Studio Intep. We offer passive house architecture and, in general, real estate efficiency and life cycle optimization services to the building industry in general. Today, I want to talk about the 2000 Watt Society and Passive House, how those two approaches can deliver great results when it comes to the life cycle impact of buildings and how we approach the carbon footprint in the built environment. The goal generally at this moment in time is to get to carbon neutrality for buildings. And why would we do that? Well, we have a climate change problem that we need to tackle, and buildings are a big part of it. Our experience is focused mostly on cold climates, so heating dominated climates. And so this is an issue that's very near to our heart because heating traditionally is provided with the help of carbon-laden fuels, and there's a carbon footprint that happens there that we're trying to eliminate. And the way that we can tackle that is with a vision. And the vision in this case is the 2000 Watt Society. I'll get into that in a moment here. And then there's an action that follows the vision, and that action is Passive House, a voluntary building energy standard. So what motivates us at the moment is, of course, the latest IPCC report. They issued a red alert. I don't know that I need to expand on that. I would assume that anybody watching this is already well aware of the situation that we face and how swiftly we need to move in the built environment to help with carbon footprint. One quick slide from the IPCC report shows that business as usual is, could lead to disastrous results for humanity. And even the most optimistic of reduction pathways still mean that some of the climate change that's here will be here to stay, and we will have to adapt. So there's urgency, and there's good reason to investigate climate footprint reduction in the built environment. Our offices practice in the United States, and we define our climate Olympics as getting in line with a sustainable carbon footprint, globally sustainable carbon footprint. Generally, that's thought of to be 1 ton annually per person. There's some debate over that. It might be 2, it might be 3, it may be a half a ton, but it's certainly down there at those ranges. And the US average generally is about 20 tons. So that's our climate Olympics. We need to figure out how to do what we're doing today within that 1 ton budget while maintaining our lifestyle and everything else as much as we can. So the vision that we use for our approach is called the 2000 Watt Society. The tagline here is one target for all. It is not expressed in a carbon footprint, but those two relate. So the concept behind the 2000 Watt Society is that we look at the continuous energy footprint above every citizen's head. And generally what we find is that 2000 watts of continuous energy per inhabitant of spaceship Earth is a sustainable number. So that would be the same whether you're living in the United States and Germany or some other country around the world. And how that's generally achievable is with one strategy for all, and that strategy reads efficiency plus sufficiency plus renewables. So we have to use the energy that we use smartly. We cannot afford to waste it. We need to make sure that we use it for the purposes that it's intended to, and that we don't oversize those items. So in the case of buildings, we only want to build as much as we really need to satisfy our need. That's a great way to get on top of it as well. And then lastly, renewables. All of it will be powered by renewables, meaning no carbon footprint for the energy used. And the renewables can really shine when they are built on top of buildings that are sufficient and efficient from the get-go. So coming back to the United States, if we express the energy footprint of a United States citizen in the same fashion as the 2000 watt society does it, we're looking at about 12,000 watts in the United States per person. And as you can see in this graph, 1,250 of that already comes from clean energy today, and about 10,750 is still carbon-laden or non-renewable fuel. And so this creates some realities and some opportunities. We put that in perspective here with a couple of different places around the world, and then the 2000 watt society on your right. Our office is located in Minneapolis in Minnesota. Urban environments tend to have a slightly more favorable energy and thereby carbon footprint per capita. You can see that's already reduced significantly from the 12,000 to 8,100 roughly watts. With a small amount of that pie shape coming from clean energy and the rest of it still being non-renewable. The data set here is a few years old. This stuff is getting better. Obviously, we're building a clean grid, and so the green pie wedge is growing. But the point is, it's still a large energy footprint, and the majority of it is non-renewable. Now we look at cities in Europe that have leveraged the 2000 watt approach to see how they're doing. Arguably, we have the same, if not maybe a better quality of life in places like that as we would in Minneapolis. So we look at Munich, for instance, where their overall energy footprint is already much reduced. But still, we have a fairly high non-renewable energy content there versus clean energy. And then we look to Switzerland, a city like Zurich, that has about the same energy footprint, but is further along in the development of the green grid, and almost half of the energy there per capita that is consumed comes from renewable or clean resources. And again, the reference on the right is the 2000 watt society, which is believed to be an ultimately sustainable footprint for our spaceship Earth. So in order to transition to the 2000 watt society, we have to understand and agree which path we want to invest in. There are two fundamental approaches here. One is substitution. We simply make the clean grid as big as it needs to be to take care of the entire pie, or we follow the 2000 watt society paradigm and we shrink by our energy footprint by being smart about how we use it and what we build for, and eliminate wasteful energy use and focus then on the remainder of that as a clean energy. And by the way, there will be most likely some small carbon footprint, and more or less indefinitely. And under the paradigm of the 2000 watt society, again, that is sustainable to have a small carbon footprint per capita. I'll give you a couple of examples. So as we're at these crossroads, let's look at two places and how they are responding to this. The first one, our hometown here of Minneapolis, is currently on the track, and I suppose I could say that for the entire state of Minnesota, we're on the track of substitution. So what does that mean? Well, we're looking at a graph here that sort of aggregates all the different energy consumers in the city of Minneapolis. And so the current energy use, as you can see, has peaks and valleys and is clearly dominated by heating energy as we're in a cold climate zone. That's that gray big bulk right on top of the graph. So in January, we experience our peak load. And then in the summer, when everybody's air conditioning, because it also gets warm and humid here on the flip side of the season, there's a smaller, much smaller peak load. In reality, the mobility curve may grow a little bit in the winter months as well, because we heat our cars and the lights are turned on more, but you get the gist of what's happening here. So peak load clearly happens in the winter. So if we look at the current clean energy plan for the state of Minnesota, which says substitution, electrify everything. So we put heat pumps in buildings and fuel our vehicles with electricity. We have two significant challenges here. One is we have peak heating, a massive peak load right in the dead of winter when solar and wind may struggle to get on top of these loads. Solar in particular, because we have a snow load and days are short. Wind may still work fine in the winter, but you can see that peak is also very seasonal. And so to build a green, clean grid that gets on top of that peak heat load means we would have to build a massive clean grid. We're showing here one curve just to get on top of the summer cooling load, and that's already significantly larger than what's currently produced in clean energy. And so you can see where we're going with this train of thought. This is going to be a very expensive track, and it's also going to be a track that is not very resilient because we still rely on that energy being made and transferred. And so the consumers themselves, buildings in this case, are not very resilient at all. They still rely on this input. So a perhaps better clean energy plan, as our firm suggested to the city of Minneapolis, would be an efficiency first approach with retrofits and passive house for buildings. And you can see here, if that were done successfully to the built environment, the peak heat demand is reduced significantly. And actually the curve for the current clean grid build out looks quite favorable. We still have a seasonal load shifting challenge. But in general, we're getting much, much closer with the build out of that clean grid, the cost that is invested in that, and what it is able to provide. In contrast to that, let's look at Vancouver, the city of Vancouver, who we advised some years ago. They're not in a cold climate zone, so it's a slightly different place, but we're talking about paradigm at the moment. And Vancouver decided to look at and pursue the path of sufficiency, efficiency, and renewables. Let's look at what that means. So first of all, we have an energy flow. So we extract source energy on the left-hand side here, carbon-laden or renewables for that matter. We pay at our meter on site, and we do all that to satisfy our need, which is things like transportation, light, heat, cooling, hot water. So that's the general energy flow as it exists today and will continue to exist. So the whole reason why we extract and do source energy is to provide what we call the useful energy, and in this case, in our buildings or for transportation. Now, the challenge we have is that the current paradigm of using these carbon-laden fuels predominantly for this is just simply not sustainable. So we need to change that paradigm over to a sustainable system in which we do more with electricity and renewables on the front end. And so in implementation for a city like Vancouver, we came up with a carbon framework plan that is again based on and inspired by the 2000 Watt Society, efficiency plus sufficiency plus renewables. And for Vancouver specifically, that means reducing the energy footprint by about 50% and then eliminating all fossil fuel consumption and replacing it with a new clean grid infrastructure. And Vancouver is currently doing exactly that. And in the built environment, the way that they're tackling it is with the passive house approach. This is a screenshot from the City of Vancouver's website that talks about high performance building standards as they're mandated today. And in this particular case, they're using the passive house paradigm, which we'll talk about next. Passive house is based on 5 basic science principles, and those are thermal insulation, passive house windows, heat recovery ventilation for the building, airtightness, and the avoidance of thermal bridges. We won't have time today to go too deep on this, but it basically means it's a really, really well-made, high-performing shell for the building that emphasizes heat retention, clean air, and free passive solar heat gains when available. The paradigm shift can also be paraphrased for our cold climate in this image here, where existing and older buildings in particular ultimately behave like a tent with a big old power plant in them. And we're replacing that paradigm for the cooler box here, signifying a highly insulated envelope, the vacuum bottle, the thermos bottle, signifying airtightness. And if we have a building that is built to that standard, we can use that candle, a very small heating source, to achieve the same thing and heat that volume. And why would we do that? Well, these useful energy reductions, here shown on the right-hand side, light, heat, hot water, if we can be very efficient and need very little of those on this side of the diagram, then we have typically a multiplier that spools up and we reduce massive and bulk amounts of source energy on the front end. So in the case of heating energy, if we use electricity, the grid has some kind of an inefficiency where, depending on where you are on the planet, maybe only 1 out of every 2 or 3 kilowatt hours that are produced will actually reach you in the form of useful heat. It could be worse, perhaps even. And so again, every kilowatt hour of useful heat in the building that isn't needed may equate to multiple kilowatt hours of energy that doesn't even have to be extracted and converted. And so this is where passive house as a paradigm shines. We reduce the useful energy and spool up a multiplier on the front end to reduce source energy. And by the way, when we do that, those benefits start to multiply, because when we provide energy efficiency, also by extension, we reduce climate impact. We increase human comfort. We will have much more thermally comfortable spaces. We increase resiliency. Those buildings do not rely on the input of energy as much as conventional buildings. Durability is also increased. An airtight structure that is field tested for performance will generally last longer and have less maintenance than a building that is not. And then ultimately, this also means something for life cycle cost, because we're reducing a huge amount of the operating expense, and that happens over the life of the building, meaning that the life cycle cost efficiency of a passive house is much, much greater than the status quo. So let's get into a couple of examples that teach us some valuable lessons. First one, all of them here learning from Minnesota, US climate zone 6 cold and 7 very cold. The first one is the Waldsee BioHaus, an environmental learning center in Bemidji, Minnesota. That's climate zone 7. It was built in 2006, and it is the United States' first certified passive house in the United States. When we designed it, the brief called for a place where students can live and have classes. There's 2 classrooms and about 20 children, and their teachers can stay in this, and it is part of a larger campus for university language campus. I won't have time to get into all the stats for the building, but I will leave this up and perhaps you can rewind and look at this. This gives you an idea of the performance of the building envelope items. We talked about much increased insulation in the walls, slab and roof, much better windows and doors, high efficiency heat recovery ventilation, and airtight building. And as a result, we get a really, really small heating load and a very low primary energy demand. And this is all energy modeled, of course, with the Passive House Planning Package energy modeling tool. After 10 years in existence, we went back to the Bio Haus and we did a quick analysis. And as you can see here, what we learned is that the PHPP said that we would have an energy footprint of about 30.6 kilowatt hours per square meter year of site energy. And the building performed basically on point with very small fluctuations for most of those 10 years, with the exception of the first year where there was still some construction happening. So learning from the Bio Haus, we find that, first of all, it was a trailblazing project. So we showed that in a very cold climate zone, passive house can be applied, and it actually works. The building has been built and it's operational for over 15 years now, and it demonstrates that the energy efficiency strategy delivers actually 90% reduction of heat load compared to the baseline of buildings that are built in our general area. We move on to our second example, the Good Energy House. It's a single family home. It was completed in 2020, and it is the first Passive House Plus. Plus meaning that it has a renewable component that is part of the energy balance sheet. The Good Energy House was built as a demonstrator by our firm, but it also happens to be my own home. So I have a lot of anecdotal information about this project if we ever get a chance in a workshop setting to chat more. Again, I'll leave this slide up for just a moment and hope you have time to read this on your own time. You can see the building envelope and other improvements. And I would call attention again to a very low primary energy demand of 80 kilowatt hours per square meter year. and a very low PER demand, which is a metric that signifies the carbon impact by extension in the passive house paradigm of 37 kilowatt hours. Also, this building with its solar panels on the roof and the predicted generation of 104 kilowatt hours per square meter a year will be a plus energy building, as the name suggests. So over time, we're looking at peak loads, we're looking at heating loads over the winter, the building is fully monitored, and we're looking at the on-site offset. And when we keep an eye on that, we can learn from the Good Energy House that the peak heat load reduction that was suggested is achieved, and that the on-site renewables provide 100% of the annual site energy consumption, and that even includes charging an electric vehicle. So the passive house delivers a sustainable cold climate performance, which again is what we're after in this paradigm of efficiency and sufficiency. I should also note that it's a 4-bedroom home for a family of 4 at about just under 200 square meters of living size. So it's not huge, and that goes back to the sufficiency aspect. Another residential example, the Minne house, was the very first cold climate passive house retrofit. Passive House calls that EnerFit. It was a pilot project that was done in 2012, where the house was converted from a 1935 single family home to a certified passive house. We're not going to go very deep here, but we want to leave you with a lesson learned from the Minne house, and that is that the passive house retrofitting also works in a cold climate zone. We were able to retrofit the building to the performance criteria set forth by the Passive House Institute, and the performance in the real world measured at the meter is actually very near what new construction passive house delivers. So the good news here is we can retrofit and achieve a similar, very, very similar result, and it works in a cold climate zone. From here, we advance to larger buildings, hook and ladder apartments, affordable multifamily housing in Minneapolis, done between 2018 and 20. Our work actually preceded the construction a little bit. It's a new construction multifamily building with about 55 units. And some of the observations here are that the site energy is once again reduced significantly. So we're looking at about a 2/3 reduction over the status quo if it had built to the current energy code, which is significant. And that also leads to energy cost reduction. Now, a building like this will be all electric to fall in line with the clean grid. So no more burning of fossil fuels, no natural gas infrastructure. And so the energy cost reduction is perhaps not quite as great as the energy savings, because in our area, natural gas is a lot cheaper per kilowatt hour than electricity. On the source energy side, remember the graph, we're going from the useful energy back to the beginning of energy at the source energy. We see a similar reduction of about 2/3, and the CO2 savings, they can be significant, again, depending on how this building is fueled, but anywhere from 40 to 75%, depending on what we measure and how we measure that. I think in general, it would be fair to assume that we're cutting the carbon footprint of these buildings in half when we build them to the passive house standard, and that is before we throw renewables at it. So that's looking at a conventional grid mix, which in Minnesota is still dominated by fossil fuels. The point that I'm trying to make is that this will go much, much higher and has the potential to be 100% when we connect to an all clean grid. The hook and ladder building actually has solar panels on the roof, but in the initial reports, we weren't looking at that as to help us with efficiency. And then last but not least, the cost savings are also there. So this is affordable housing in Minnesota. Those owners have to hold the buildings for 30 years. They're leased to people with subsidies. And so we find that we can see anywhere from 3 to 8% annual annuitized life cycle cost improvements, even under current conditions. So that's current electricity and utility costs. that's looking at things like refurbishment that come into play, and that's why sometimes those numbers are negative when we reach points where we have to make an investment again. But the point is, and this is where developers perk up, is that especially if they hold these buildings as they do in affordable housing, this is actually savings towards their baseline. So the main lessons learned from Hook and Ladder is passive house works for larger buildings in a cold climate zone, and the annuitized life cycle costs are better than business as usual. So we have a good example here. And then we get to one more example, which is affordable housing retrofitting. Elliot Tower, also in Minneapolis, Minnesota. This is a retrofit of a, I believe, 14-story building, all affordable housing, so subsidized housing, exterior and interior improvements. And the main takeaways here are, again, energy and load reduction. Now, the existing building is virtually uninsulated, so we're providing a heating energy reduction of 94% by using the passive house paradigm. Cooling energy will go down 30%, and I should say comfort is going to be increased incredibly on both sides of the seasons here, because the building will be insulated and airtight. We can be much more efficient with how we do domestic hot water and even reduce some of the auxiliary and plug loads in the building. Site energy cost and CO2 savings go right in line. So with this project, energy consumption on site can be reduced by 3/4. The site energy costs by about 60%. Again, gas being cheaper than electricity, it doesn't quite track along at the moment, but it's still significant. And the CO2 impact of this building will also be reduced by well over 50%. So learning from Elliot Tower, we can see that passive house retrofitting works for larger buildings in a cold climate zone. The heating loads can be reduced in excess of 90%, and the CO2 be reduced by over 50% before we account really for renewables. And this fits the paradigm of a green grid much, much better. So I will conclude by telling you that the 2000 watt society with sufficiency, efficiency, and renewables, and a target of 2000 watts per capita is an effective strategy for climate neutrality and the clean grid optimization. Passive House supports the 2000 watt society energy target for the built environment. So those two have a really nice handshake. In Minnesota, in a cold climate zone in the United States, we have examples from the last 15 years that illustrate that the concepts are applicable, even in this very cold climate zone, and they provide peak load, CO2, and life cycle cost optimization in a very cold climate. In addition to the environmental benefits, we have another perk that we haven't really talked about today, but it is worth considering. We have an opportunity for economic growth because this work needs to be done. We need to train people to do buildings right and retrofit them at scale. So there's an economic growth opportunity. And I think in particular, when we're looking at affordable housing projects, as shown in these examples, there's also an opportunity for social justice, where people of lesser means quite often live in quite substandard living environments. And so by retrofitting in particular and building new for affordable housing with the passive house standard, we significantly elevate the status and therefore provide a significant contribution to social justice. With that, I thank you for your time. I much appreciate the opportunity. I welcome any questions if we have a platform for an exchange, and I wish you all the best with the summer school. Thank you.